Recording. All right, welcome everyone. Thanks for joining our 9th AMA Ask Me Anything series. This is this was created by the ASB Student Committee to provide a space for, like, a casual space for students who recently published to talk about their work and for everyone else to kind of ask questions. And it's not just, we've built this so that it's not just a typical research talk, but we're actually talking about lessons learned or issues we had in publication. And sometimes there's just a lot of ins and outs that advisors kind of just like know because they've been doing this so long, but we're all learning. So we're learning from each other. So today we have Jenny Leestma hosting, and she'll be talking about a recent publication and some of the stuff she learned from that. So how this will go, Jenny will talk and share some slides for 20 to 30 minutes. And then we'll open it up for discussion and Q&A. And then the last 10 minutes, I will stop the recording so that if anyone wants to ask a question not on the recording, they can feel free to do so. Feel free to post questions in the chat as well. All right, Jenny, take it away.
I'm going to hope it's 20 to 30 minutes. I might end up like doing a rapid pass or skipping a couple sections. If
that's okay. More discussion.
All right, so thank you for having me, and thank you everyone who's on for coming. This is always kind of exciting because I feel like we all learn a ton as PhD students through the process. So to have a bit of a mechanism to share some of this is kind of fun to share some of the lessons I learned in this first kind of big study that we did that was the first major one for my dissertation. So the title of this talk is Lessons Learned from Perturbing People, Researching Recovery and Communicating Conclusions. And as Anna mentioned, my name is Jenny Leestma. I'm currently 4th year going into my 5th year in the robotics PhD program at Georgia Tech. So let me make sure I'm advancing here. Great. So I'll start like some of the other candidates did in previous talks and give you guys a very brief rundown, kind of rapid pass here of how I landed at Georgia Tech. So I was born and raised in a suburb of Minneapolis, Minnesota, and I jumped over to the University of Wisconsin-Madison to do my bachelor's degree in biomedical engineering. I was really interested in high school in math and medicine, and I kind of was exposed to prosthetic limbs when I was a sophomore. And that was, you know, kind of my best guess is what would let me work in that field. So I was very lucky to get my first internship at the Minneapolis VA hospital. I worked in an kind of a adaptive device and engineering group where they worked on a lot of different rehabilitation technologies. And this was such a great first experience to have because they did a little bit of everything. They were doing rehab technologies, exercise equipment, medical devices, prosthetic limbs, sockets, all that kind of stuff. So the areas of BME that I was interested in, I feel like I got to kind of get exposed to all at once. So I was there for a couple summers, but I was really interested in digging further into prosthetic limbs specifically and biomechanics. So back at UW-Madison, I got to join Peter Adamczyk's lab and spend about 1.5 years working with him. So there I focused really on lower limb prosthetics and a variable stiffness foot that you see here, as well as some kind of sensing and lower limb biomechanics of using this device outside the lab environment in different locomotion modes. So this is really what got me into this idea of how do we adapt devices and get them to act differently in different environments. And the way that that happens a lot of the time in wearable devices and robotics is adding a little bit of intelligence. So kind of the next step I took was I was able to get an internship in the Center for Bionic Medicine in Levi Hargrove's lab at the Shirley Ryan Ability Lab. And here it was a lot of discomfort in terms of the stuff that I jumped into. So I was doing upper limb stuff. I was doing myoelectric or EMG pattern controlled upper limb kind of prosthetic applications. And we were doing things in virtual reality. So I learned a ton in this summer and figured out that I really wanted to have this kind of intelligence component in the loop in grad school with all of the lower limb biomechanics that I was still kind of interested in sticking with. So before I wrapped up and went to grad school, between graduating undergrad and going to grad school, I was able to get an industry internship, which I was really interested in doing. So I worked in the biomechanics R&D group at Össur in Reykjavik, Iceland. I didn't actually work on the top foot. We were working on a kind of a derivation of that foot that was kind of meant for more diverse activities. And then I worked on a component for the foot on the bottom there. So that was really kind of a nice exposure to the current state of prostheses that were available commercially. And then finally, I landed in two labs that absolutely captured all of my interests at Georgia Tech. I work in the EPIC lab, or the Exoskeleton Prosthetic Intelligent Controls lab with Aaron Young, and the Power lab, or the Physiology of Wearable Robotics lab with Greg Sawicki. We love our acronyms here. So I'm co-advised in both of these labs, and it's really kind of the perfect blend for me of lower limb biomechanics and sensing and intelligence, and kind of have a nice mix of wearable robotics with a lot of physiology and biomechanics input, but also getting into some machine learning and some things like that help make these a little bit more intelligent and adaptive. Okay, so the overarching goal of my entire dissertation is to make robots, and wearable robots specifically, that can augment balance during walking. So when starting this, the ways that we were kind of thinking about this is, if you have someone walking, there's a couple biomechanics components that we really needed to study and be very familiar with. And the first one is, how do you perturb people in the lab? How do you actually get people to lose their balance consistently so you can study it? And then the next step was, how do these actually different kinds of perturbations affect people's balance in response? And then lastly, how do they actually recover their balance and get back to steady state walking? So there's kind of a flip version of everything we need to be considered when we move to an exoskeleton that I'll kind of mirror here. So how do we detect a perturbation? So how do we know when someone starts to lose their balance, and we might need to kick in either an exoskeleton controller from them not having anything, or kind of kick into a different mode that's meant for balance augmentation? How do we actually model and predict and understand what the human is going to do so we can develop an exoskeleton controller that kind of works with them and doesn't fight their natural response? And then lastly, how can we actually apply that controller to get them back to steady state gait? So the first questions that we wanted to address in my dissertation were, how do diverse perturbations affect balance and recovery strategy? And how exactly were we going to get to perturbing someone? So I'm going to do a very rapid pass at the paper here, and I'm happy to talk about anything in detail if you guys haven't gotten the chance to read it, or even if you read it and you still have a lot of questions. So the paper that I'm talking about today is called Linking Whole Body Angular Momentum and Step Placement During Perturbed Walking. We published this a few months ago in the Journal of Experimental Biology. And the reason I think that this author group was kind of fun is Paul Galiski was the older grad student that really mentored me when I came into the lab, and was a big part of kind of getting me onboarded and helping me with this project. And then Courtney Smith was an undergraduate mentee that worked with me for 3 years and actually ended up spinning out her own independent project from this work. So it was kind of cool to work with people on both sides of that. And then, of course, my co-advisors, Aaron and Greg, were both on this. So the first main goal of this paper was to introduce a novel multivariate perturbation paradigm and the associated open source data set. So really what we were trying to do here is, how do we perturb people in a consistent manner, but also we wanted to get a really big diversity of perturbations so we could understand some of the overarching trends that exist across a lot of different kinds of instability. So the way that we decided to do this is, we have this big platform system that I'll show a little bit later in our lab called the Karen system. And basically what it is it's a instrumented treadmill bolted into a big platform that can move in 6 degrees of freedom. So we can basically take the entire treadmill and rapidly shift it in space, or rapidly rotate it in any direction. So using this, we wanted to try to figure out, how can we come up with a bunch of different mechanisms with which people might lose their balance and perturb them in a bunch of different ways, so we can analyze kind of these overall relationships that we were interested in getting at. So the way that we did this is, we perturbed them in 3 different magnitudes. So basically the overall distance that platform moved, that kind of scaled with the velocity and acceleration as well. So basically, how big did the perturbation feel? We perturbed them in 8 different directions. So we kind of slid that platform underneath them. And then we also perturbed them at 4 different times during their gait cycle. So we were able to control exactly when the perturbation onset. And so this was kind of step number 1, is develop a perturbation paradigm to get at kind of this huge diversity of perturbations that we wanted to look at. Okay, next was to evaluate how perturbation magnitude, direction, and onset time affect stability and recovery strategy. And these graphs start getting more and more dense. So I'm probably still going to go over them quickly, but I'll tell you the main takeaways. So to do this, we wanted to evaluate a balance metric, and we went with whole body angular momentum, and specifically the integrated version of the signal over a step. Be happy to chat about this more afterwards. And so what we're just really showing in this figure, which is the second figure in the paper, is we wanted to make sure first that these perturbation conditions were actually kind of varying the outcome measure like we expected or anticipated that they would. And you can see here, we kind of given it different spread depending on the direction of the perturbation, which is shown in the different colors. And this is just an example of what sagittal whole body angular momentum looks like during the step at which they were perturbed, which is the dashed line. So we looked at this during the step that they were perturbed and the next step, and you can see we get a pretty good spread of effects of this perturbation condition. And then we also did this in the frontal plane. And then to kind of collapse this metric and make it digestible with a single number and not a time series, we ended up integrating this over the step, comparing it to the steady state data and quantifying how much it changed from the steady state values that we were seeing when they were not being perturbed. And then we did the same thing with step placement. So here you can see this one's a little bit easier to understand because we're just looking at a bird's eye view of, imagine people had chalk on the bottom of their feet and they're leaving footprints, and you're seeing where their heel marker would have been in different locations as a result of those different perturbation directions, which are the colors. So again, we looked at the step that they were perturbed in, as well as the recovery step. And then again, we collapse this kind of relative to their steady state walking data to get an idea of how much did their step placement change relative to kind of their usual walking. So this is where the graphs started to get really complicated, and I'll talk a little bit about the figure process later, but there's kind of a lot to digest in these figures. So I'll animate things in, but first we started with how was integrated whole body angular momentum affected by these different conditions. So first we looked at how magnitude affected these in the perturbed and the recovery step. And we just bin these into kind of no response, small, medium, and large amounts of instability. And I didn't actually include it in this presentation, but we also saw jumps in a very, very small subset of these perturbation recovery strategies, which has spun out into its own side project that we're looking into. So we looked at this for magnitude, we looked at it for timing, and then direction. There's quite a few of these, but relative to the foot, the platform's being pulled to those pies. So it kind of gives you an idea if it's off to the right of the foot, that means the platform was pulled that way, and they tend to be falling to the left in that case. But overall, what we were seeing is higher magnitude is worse. Not a big surprise on that one. That was a nice validation that we were seeing what we were expecting. Timing had some interesting conclusions with earlier times being better in one step, but later times being worse in the next step. And then the same thing with direction. We saw medial-lateral perturbations are really a lot more challenging, specifically ones that kind of push you to the side, but also kind of pitch you backwards a little bit. And then we did the exact same thing for step placement. And we saw a lot of the same trends that were leading us into one of our hypotheses, which there's some interaction between these where step placement is really potentially a function or related to how much imbalance they are experiencing. So the last one we really wanted to look at was to investigate this relationship between stability and recovery strategy. So we wanted to look at, in the frontal plane, basically the integrated whole body angular momentum versus the step width, and the sagittal whole body angular momentum versus step length. And so here we looked at frontal plane WBAM versus perturbed step width for a certain perturbation timing. And you can see we see a pretty strong correlation between these two, and definitely some nice clustering of the different colors for certain perturbation directions. We did this for all the timings, and you can see with variable correlations. Happy to talk more about this. And then we also did it during the recovery, that one. Yeah, so we also wanted to look at these correlations for individual subjects. So we looked at the overall, this is all the subjects on the scatter plot, and then we have the individual subject correlations on the far right bar plot. And we also did this for the recovery step and generated the same graph. And really one of the big takeaways here that has really made me pause on the way that we're processing a lot of this data is a lot of lessons we learned about not collapsing data on all of your subjects together too fast. So if I bounce back a couple of slides, what we originally thought we were seeing in some of these, can you guys see my mouse? Let's see, over on the screen, yeah. So we originally thought this was just kind of some messiness and not super strong trends that we were seeing here. But what we were really seeing was one subject had a really steep slope kind of going through the data like this, and another subject had a much shallower slope going through the data like this. And so by collapsing all of it too quickly, we were missing out on the fact that some of these correlation strengths were a little bit stronger within certain subjects. And then we also did this in the sagittal plane. Correlation strengths were definitely not as strong in the sagittal plane because we think the ankle handles things a little bit more than step placement deviations. And so, like I said, that was a super quick overview, but I'm just going to highlight some of the main takeaways that we really kind of gleaned from this study. And it was the effect of perturbation conditions significantly affected both of our outcomes in both the perturbed and the recovery step for everything that we looked at. And one of the interesting things that I detail in the paper that's not necessarily visualized in these figures is there's some really interesting interaction effects, specifically between the direction that someone's perturbed and the time during the gait cycle at which they're perturbed. So that has made us think very carefully about next steps and how we compare different perturbations and what we expect people to react like. And then also the relationship between WBAM and step placement is much stronger in the frontal plane. These relationships did have a significant influence of timing. As you saw, the correlations going across to the right were not nearly as strong, and that has to do with how much of their step they're unstable for, and we think some things about reaction time and how quickly they can modulate where they put their foot. And the within and across participant differences is something that we're definitely very careful to look at now because people don't necessarily respond to perturbations as consistently as we're used to in our lab with things like steady state walking. Okay, so that's the paper part. I was trying to get through this really fast so we could talk about some more of the fun things behind the scenes. So behind the scenes. So coming into the lab, I think I had this very idealistic version of writing a paper in grad school where it's gonna be like, okay, you come up with an idea, you pilot it, you collect, you process, you analyze, you write, and you publish. And especially because I had done some stuff in lower limb biomechanics, and the later part of my PhD is more in machine learning and exoskeletons that I was less familiar with. I was like, okay, the first paper, we're going to get it done. I'm going to do it in a year, and then I'll get to the stuff that I'm like super unfamiliar with. And that did not happen. This paper came out 3.5 years after I started. And I wanted to kind of unveil a little bit about some of the stuff that was going on behind the scenes, just kind of for the sake of transparency and hopefully starting to break down that this is not how the publication process goes. So pieces within this that I was not expecting. First, we had to learn how to use this massive system that was called the Karen that I got here the same week that we were trained. So it was a brand new system when I started my PhD. And so we had to figure out how on earth do we control this thing and run an experiment and integrate everything together and build and validate this entire experimental paradigm. Then when we piloted, we figured out, okay, when you have force plates in this like massive, hundreds and hundreds of pounds platform, and you're accelerating it in space, F equals ma comes back to get you, and you get these massive induced forces on the force plates when you're moving this thing. And I'm talking about like 600 newtons in the AP and ML directions. So that is not stuff that we could ignore and still do inverse dynamics. So we went through the process of finding a method and building off what another lab had done to correct for this before we even started collecting our data. We had to figure out how to run this entire thing through a closed loop controller, since we were doing that real-time kind of gait cycle tracking to target when the perturbations were happening. We had to get a whole closed loop controller going with marker data. And we also started to evaluate some of the different balance outcome measures to really get our feet wet in that area. I'm skipping because collection went surprisingly well. And that is not something I ever thought I would have said. I thought that was going to be the pause point. So I'm knocking on wood. I think it's probably going to come back to get me in a later study. But then once we got to processing, we worked on semi-automating this processing. It was a pretty large data set, but that's something that I also wasn't expecting, is just the pure amount of time that it would take to automate this, especially with marker filling and gap filling and all of that kind of good stuff. We also had to throw out some participants. When you don't have a diligent checklist, you will forget markers when you are running a 75 marker collection. So I left off a couple really important markers in 1 or 2 subjects, and it just wasn't salvageable with the way that we were doing our inverse kinematics and dynamics, or we weren't comfortable with putting them all together. So we collected some more. Visualizing 3 different independent variables took a very long time. I'm going to cover that a little bit. We had to visualize a lot and choose a few. We were validating the way that we were calculating whole body angular momentum because we did it with our own code out of OpenSim. And then we also collected more participants because we were prepping for using this data for a machine learning approach where you need a lot more data. And then in the process of revisions, I ended up rerunning the data 4 times. I found 5 trials out of just over 3,000 where we hit an OpenSim range of motion edge case where the limb got stuck and popped back into place that I really didn't want to be in there, especially since we were open sourcing this data set. So turns out when you do this, you need to undo both shoulders range of motion. So I did one, I reran the whole thing and I was like, oh my gosh, I forgot to do the other one. Did the other one, another week and a half of running the data. And then finally we got to open sourcing the data and putting out this paper. And one of the other things I want to highlight is just all of the fun things that affect your timeline that no one tells you about either, and all the things that pop up that make this such a nonlinear process. So we were figuring out how to sync all of our equipment, and that took months to figure out how to integrate everything together. Red is going to be things that were not so fun. Green were things that were pretty fun. So collaborating with another student on a paper that spun out of this project. We got hit with a global pandemic after I collected my pilot. Not a thing I thought I would ever say about my grad school experience. Took the hardest class I have ever taken by far and felt like I didn't do any research for a semester. Everyone has equipment maintenance, so that was putting a wrench in our expected timelines. We discovered an unexpected recovery strategy that we spun out into a side project. It also led to collaborating with bipedal robotics lab on campus that took some time. I joined a completely unrelated project to my dissertation that took some time away from this kind of mid-collection. Had undergrads that were starting to work on separate analyses for their own projects. I ran so much data and did not consider that my computer was filling up, corrupted my motherboard, and had to completely set up a new computer. And you don't realize how many MATLAB paths and software packages you have that are integrated on your computer until you have to set a new one up from scratch. And then we started the same study in a clinical population that a postdoc in our lab was leading. So these were all the fun side things that completely derailed the expected timeline. Okay, so then the next part. How did we actually do this? This was kind of one of the biggest challenges in this entire data set, specifically this perturbation timing. And this is, again, kind of unveiling what's behind the scenes. I sat at this desk for probably about 6 months trying to get this control loop paradigm to work. And this is an example of what this whole controller looks like. And within each of these little boxes, there's code and a code language I had never heard of when I started grad school called Lua. So learning how to use that was a new adventure. And this is kind of, even though it doesn't really go into papers, because as long as the paradigm works, you just have to explain the output, not the way it's necessarily working behind the scenes and how everything is connected. This was a huge part of my PhD that, again, I don't think I was accounting for how much buildup there can be in experiments like this. So here's the result. I'll just play this video for a second. So we were able to perturb people in a bunch of different ways, and this is what led to the data set. And I'm going to start speeding up because I feel like I'm going to go way over a half hour. So this data collection ended up being 96 different conditions. We did 3 repetitions of each condition per participant. We had 11 participants. So we landed on somewhere just over 3,000 perturbations. And the fun in data processing is this was just over 10 hours of collected data. And we collected quite a bit. So definitely have learned a lot of tips and tricks for managing a large data set, especially when this is one that we were open sourcing. So I will talk a little bit about that process in a second. So lessons learned from data collection, just a quick high level points. Full automation is not always the best. I have found that somewhere between partly manual and partly automated processing makes me feel like I'm able to catch enough of the errors that might exist. You won't write it down later. So when you're collecting a study and something happens and you say, oh, I'll write that down once I get back to the desk, you will not remember. So this was a lesson learned when I went back to this data and was reprocessing things a year later. Give yourself some pilot data for the next study that you're thinking about. Biomechanics data is really time expensive to collect and process. So if you can think about what your next step is and build some of that into your existing study, this is a great way to kind of tee yourself up for a slightly, slower burn in getting a next project going when you already have a little bit of data to work with. Sometimes, only sometimes, reinventing the wheel is easier than adapting the wheel. So I went through a lot of battles with, do I try to use other people's code or things that I could find online, or do I just start my own from scratch? And I think it can be a lot easier to go back, find bugs, edit code when you've done it yourself, even if it might be more time intensive. And the documentation, the commenting, everything like that is not necessarily always great, even if code is available online. So this is definitely something I go back and forth on a lot, depending on the application. Okay. This was a big lesson learned in this process. Was don't underestimate the power of figures, and specifically that the road to coherent figures across especially 3 independent variables is a long process. So this is an example of, I don't think I got all of them, but a lot of the figures that we tried along the way that never made it their way into a paper. So we were really trying to get our bearings and understand how these different variables were affecting things, how variables were interacting when we were looking at balance and recovery strategies. And it took a lot to let go of these figures and accept that they were never going to go anywhere. But we learned a ton throughout the process of looking at this in so many different ways and really getting our bearings with the data. So the lesson I had a hard time accepting was that more is not always better. I think what we learned is you understand your own data so well after sitting there and thinking about it constantly for 3 years. And as much as there is cool data you want to communicate, if people aren't going to get it in, the 20 minutes max that they have to read your paper, it's probably just going to make them more confused rather than getting your main points across. So this is already a very dense figure that we accepted people might need to stare at for a little bit to really understand and collapse all of this data across the different variables and understand the trends. Believe it or not, I still can't believe that we were thinking about this. This is the original figure set we thought we were going to put out. So this is every one of the 96 conditions has their own pi. And this is across the perturbed and the recovery step for both of our outcomes. So what should have been a dead giveaway for me is that the file I had all of these saved in was called this. So that should have been a sign very early on that these shouldn't have gone anywhere. And believe it or not, we were really stuck on this idea. We really liked it. We're like, maybe the pies are making it hard to read. Maybe we should try bar graphs. The bar graphs were definitely not better. So learned a lot of lessons in creative MATLAB plotting and really pushed my limits. But what ended up happening is we just decided people are going to be more, unwilling to read these figures than they would be to really get in and get to the information and try to digest it. So we wanted to make it a little bit more clear. So that is how we landed back on this one that is more digestible than those crazy pies. So some lessons learned about figure generation. Screenshot awesome figures for years and keep a folder of them. When you get to analyzing and visualizing your data, if you need anything beyond bar charts and time series, I think you can hit a bit of a creative block and like, how could I communicate this information? So what I started to do is every time I saw a figure that I was like, oh, this is awesome, I never would have thought of doing it this way, I screenshotted it and stuck it in a folder. And that gave me a lot of ideas for how to create, figures that looked across multiple dimensions and things like that later on. Give yourself time to develop intuition. I really struggled with this because I thought the pace of this project was going to go a lot faster, but trying a lot of things and really taking this in a bunch of different directions before we decided what way we were going to communicate it in really has helped us build an intuition that's going to be extremely helpful when we start sticking an exoskeleton on someone and make this entire equation a lot more complicated. This is one of my advisor's favorite thing to say is let it marinate. Sometimes you need to generate a figure or a result and just sit on it for a week and let yourself think about it without the time crunch, because that's when a lot of ideas can come. This is when I find if I go on long walks without my phone and I'm just thinking about things, I come up with my best ideas when I'm not actually trying to come up with an idea or come up with a take on something. code as much of your figures as possible. We're a big Illustrator lab, so we do a lot of our figure editing in Illustrator, but whenever you have to rerun a figure and you redo it all by hand in Illustrator, it's a nightmare. So figuring out to code things in MATLAB, font sizes, font types, bolding. If you haven't used the tight figure thing before, that takes subplots and it gets rid of all the gray space between them, so you don't have to deal with that later. So this helped a ton as I got to putting some of those pie chart figures together and things like that. And take a lot of pictures. All of my little walking diagrams were either, traced from pictures and experiments, or during COVID, I made my roommate walk back and forth in our kitchen as I took pictures from different angles. So I could trace like the perfect angle of someone walking and at different phases during the walking cycle. So pictures have been very helpful in having a big repository of things I can pull from whenever I need a new one. And drawing applications. Illustrator and Inkscape are great. I find for things when you're drawing slightly more organic shapes, it's a little easier to do it with a pencil than it is to do it with a clicker or a mouse. I personally have an iPad and have an app called Procreate that's really great for being able to trace right on top of figures. You can do the same layering thing, but I found that a lot easier for drawing like people and things like that are nice accessories to figures. Okay. Open sourcing a data set. I'm going to try to go through these in the next 7 minutes because I think I'm already a little bit over on my half hour. So open sourcing the data. This is all of the data that we collected during this experiment. So we did full body markers, ground reaction forces. To correct for the platform movement, we collected accelerometers, which is the method with which we corrected everything. And then we also collected 16 EMG and 8 of those had IMUs in them. And then on top of that, things that we have released or planning on releasing are full body inverse kinematics, the corrected forces, the inverse dynamics, and as well as individual segment and whole body angular momentum from this data set. So considerations for open sourcing data. This was a newer one for us. I think we had one open source data set before we put this one out. And I just wanted to highlight some things to think about if you're thinking about doing this. Options for hosting a data set. So some journals have their own hosting mechanisms. Journals have kind of a recommended or a partner hosting mechanism. Sometimes you can just go to a completely independent one if the journal doesn't have a preference. And in our case, what ended up being really nice is our local institution has their own data sharing mechanism. So Georgia Tech is the one housing our data. There are limitations sometimes. So think about if you're planning on doing this, talk to different hosts about file count limits, file size limits. We ended up not having to really limit any of ours, but they hadn't had this many files before. As you all know, when you generate biomechanics data, I think you get 7 files next to a C3D that has a bunch of information in it. Once you have that, you have MOT files and TRC files and all that good OpenSim stuff. So we were dealing with a pretty, tens of thousands of files at the end of this. Referencing, we got a specific DOI for the data set. Sometimes you can link it directly to a paper. Sometimes you might need to do it separately, but just something to consider. Licensing kind of dictates, they have questions about how you want this to be used and how people need to reference you. So that was something that we had to kind of look into the options. Sometimes you can have these repositories be private or have a password if you need your data set to be reviewed with the paper. So sometimes it's possible to get those uploaded beforehand. With the submission process, that kind of goes along with the privacy review. So when in the submission process, does your data actually need to be submitted if it is associated with the journal? And then data set versions, usually it's typical that when you publish your data set, you're done, you don't get to touch it. For our case, we have not processed all the inverse dynamics data yet, and we wanted to be able to append this to the data set later at a second version without having to generate something entirely new. And so lucky for us, Georgia Tech's data repository does allow that. And we're basically adding new versions of the data set every time we append something major. And then file naming, format, layout, all of those things that yourself 6 months ago wasn't thinking about when you're going back to look at your data now is even more important when new people are using it. And user testing within the lab was something I tried to do. So get people to go through it and see if there was anything that was unintuitive. Okay. So I'll talk a little bit about the writing process and kind of some quick lessons. Again, one of my advisors loves to say this, and it really has resonated as we went through this paper. Cater to the quick read. So if you're lucky, this is kind of how I laid it out. This is the paper. This is how most people will read it. if they're actually going in depth. So abstract, last paragraph of the intro, or at least this is kind of how I was taught to read papers, figures with all the captions, and then the last kind of main takeaways of your conclusion. So we really wanted figure captions to help these figures stand on their own. So that's why we have these kind of denser figure captions. And we really wanted to make sure that the messages were clear in these sections that people might just be skimming for instead of reading the entire paper. So we spent a lot of time on those specific sections. The 80-20 rule. I don't know if this is usually used in research, but I found this to be very true, that 20% of your time will get you 80% of the way, and the rest of the 80% of your time gets you the last 20% of the way. And I found that to be very true. Every time I felt like we were close to getting figures done and the paper going out, it always felt like it was taking a lot longer than it should. So this was a lesson in time management that I definitely learned through the process of writing this paper. I'm coining this one. I've never actually heard this, but I'm going to call it the iceberg rule, or the 10% rule, which is another painful realization that I think a lot of people in our lab have gone through, especially when putting together dissertation proposals and defenses, which is people are probably only going to see 10% max of what you've thought about, what you've done, and the thought that you've put into conducting a study. So everything that doesn't go in is paradigm and device design, the way you instrumented things, or at least they'll get maybe one sentence, validating, troubleshooting, automating methods, discarded figures that never get to go anywhere, every reason you've thought about in your advisor meetings to explain what you're looking at. So figuring out what the main takeaways are that are really useful for people was a challenge, and it's definitely hard to let go of everything that's below the surface. This is probably advice for the slightly more perfectionist people in the room. But one of my advisors said the last 15% of changes that you want to make will not affect people's ability to interpret your results. And so I wanted to word everything perfectly and format everything and make sure I had every citation I had ever thought of. And his advice was get it in during the review process and at least see what other people think first. And you can always add some of those details in. So this was kind of a way of saying, just get it out there and start getting some feedback, and don't kind of hammer it to death, just sitting at your desk with only things that you've thought about. Look up journal guidelines early. I thought my figures went in the paper as is, and I spent time getting every font size to be consistent across all of my figures, and it turns out the journal reformats them all anyways. So there are things that can really help speed up the process, like what audience you're writing to, the word count, the figure count, the formatting that's required are going to be done for you, the supplement guidelines. We also are going to put the crazy pies in the supplement, and the journal had a supplement limit, so we couldn't fit as many in there as we thought we could. So all things that I kind of wish I had looked up sooner. Leading up to writing, storyboard early and often, and potentially come up with a better naming scheme for yours than I had, or maybe just make one extended one. The way that we kind of try to run it in our lab is we sketch out figures very early and what we think the flow and the main takeaways are going to be. And that was really helpful in kind of guiding this process. Diversifying feedback on content. Don't only have people that are on your project be the ones that you're getting feedback from. So hearing from lab mates that had absolutely no idea what I was working on or were brand new in the lab really helped me figure out kind of what areas were confusing and what were the main takeaways and what we should focus on. And then my personal opinion is I don't do well with detailed outlines. This is kind of a personal take. I like very rough outlines because if I try to write sentence by sentence, I find that I tend to be a very choppy writer. And so when sitting down and doing it, I like to write whenever I hit a writing mood. I get in kind of bursts of writing mood where I feel like my words are flowing, but it's usually not when I'm planning to sit down and write. So I tried to have a rough outline so I could just go start filling in stuff whenever I felt like words were kind of flowing. And then my lab mate gave me this advice, which was don't write and edit at the same time. So explain things, give a very rough explanation, and go back and actually tailor it with citations and correct wording and exactly how you want to format it after you get words on the page. And then write like you would explain it. This is what I've been doing recently, and it's probably the fastest I've been able to put together introduction and discussion sections. I will walk around and record myself explaining it like I would explain it to an undergrad or a new student, get back, transcribe it, and work on editing from there. So I found that it's a little bit easier to kind of have it be a cohesive story and nice and smooth when I'm not trying to put down sentence by sentence, but I'm really just explaining it like I usually would to someone. And then read the whole guide for authors page. This goes back to some of the points that I just mentioned, but things like the worst feeling in the world is getting, and you're so close to submitting and you're like, I need a cover letter. And you got to sit down and write that when you thought you were going to submit your paper. So just kind of reading some of this ahead of time for the journal you're planning on submitting to. Okay, I'm on the last section. I'm going to try to go through this one fast. I talked to Anna a little bit, and they wanted to work in a little bit of info on networking and professional involvement and some of these tips and tricks for getting involved in ASB and kind of creating a community. It's fun because I think I'm going to put a picture in here and some people are on this call. So I will say I am a natural 100% extrovert. A lot of these things I have done just because I have really enjoyed talking to people and staying in touch. But these are a list of things that I think have been very helpful in making ASB feel like a community that either I have found myself doing or other people have done to me that have kind of made me feel like I'm being integrated into the awesome group of students that we have. So pop into other labs when you're traveling. This was last fall, and we had some friends from a neighboring lab that were in town for a conference, and they asked if they could swing by. Usually biomechanics labs have a lot of equipment or weird paradigms you can try. So there's usually some fun stuff to see. So that was always a nice way to connect. And there's a lot of small world things in this photo. The 2 grad students on the right are at Vanderbilt, and the 3 on the left are all in my lab. The one on the far right, I was an undergrad with in the same lab together. The guy next to me did his undergrad research in the lab of the people that were visiting. It's a very small community. And so even if you don't know people in a lab, I think people are usually super receptive to having other grad students swing by. So we do that a lot. And I think it's a lot of fun and a good way to see people when you're not just at ASB. Shamelessly recognize people. I saw someone do this at my first conference. Another grad student walked up to me and was like, hey, I recognize your face, but I can't remember your name. We follow each other on Twitter. And I still talk to that grad student to this day. And so that was such a cool way to go up to someone. And he was just so shameless and recognizing that I try to do this whenever I see people, because we all read each other's papers. You recognize people's name tags. You'll see a cool talk and be like, oh my gosh, I want to go talk to that person. And so I think I found that just walking up to someone and saying like, I saw your talk earlier, didn't ask a question, but would love to talk to you about it now. Like, do you have 5 minutes? And I think everyone tends to be so receptive to that in my experience. And I've never had anyone be weirded out that I know who they are, recognize their name. Get involved on Twitter. This is like my favorite tip to give to undergrads who want to go to grad school. It's a great way to interact with the community regularly. People are really active on Twitter in our world, and it's a great way to see papers and jobs and postdocs and things like that I think are happening all year round, not just at conferences. Ask to attend. You're usually welcome. I think most of the time, even if you think that there's a listserv that are going out to people, you're usually welcome to come, even if you're not technically on the list of whatever is going on. So the postdoc group, the postdoc affinity group has been really great. They've been doing a ton of events on starting a lab and going into academia. And every time I've asked, they are more than happy to have upper level grad students join. So this has been really nice and kind of seeing what the next steps are like. Offer to help, it's usually welcome. It's been really fun to see the student committee this year because Anna has been doing just such a phenomenal job of giving a lot of people opportunities to get involved in different events like this and planning events. And so I think there's always ways to get involved. You just got to make it known that that's something you want to do. I also got, I don't know how involved I was going to be. I ran the website for 2 years when we virtually hosted ASB, and that led to a ton of opportunities I wasn't expecting. It was probably also way more work than I was expecting, but it was a lot of fun and a great way to see what goes into planning a conference. Commend and promote other people's super cool work. I think there's nothing more exciting than putting out a paper and having people, shoot you a note or send you an email or, give you a call or something to say, hey, I saw the paper. This was awesome. Like, I have a question or just wanted to say that, like, I like this figure because there's so much that goes into these. So I had, other people do this for me. I try to do it for other people. I think it's just a nice way to show kind of mutual support amongst people of, other grad students and things like that when we get to publishing. And then send people quick notes. This has been, like, hey, I saw this paper the other day. I remember talking to you about this at a conference. Just thought you might be interested if you haven't seen it already. This is just a really nice casual way to stay in touch with people throughout the year. Again, not just at the conference. So again, this has gone both ways. I try to do this because I've seen a couple people do this in my lab. So this has been a nice way to stay involved. And then get to know grad students from other labs. This is one, I think there's some people on this call that are in this photo. This was during COVID when I think everyone was going a little nuts and missing social interaction. But someone pointed out to me once that as much as you want to get to know like the cool PIs that you've heard so much about when you're at conferences, the grad students are going to be the ones that end up being your colleagues, friends, and collaborators for the rest of your career. So I found it super fun and rewarding to get to know a lot of the people at a similar career stage. So this was a big social get together we had on Zoom really early in COVID. And it's fun how many of these people I still see at conferences and get to talk to on a regular basis. So just a fun example of ways to stay in touch with people. Okay. I'll go through these quick. Take full advantage of conference time, drink a lot of coffee, push through the tired. It's an awesome opportunity once a year. And I try to get people to stay out and go to as many things as possible. Being a bridge for others, especially if there's newer people in your lab or in the community, they're having a hard time or a little bit shy about going up to people. I always try to offer at least to help if there's anyone they want to meet or a session they want to go to that they're kind of nervous to go to themselves. This is just a lot of times for other people in my lab. And organize chats ahead of time. I went to a Growing Up in Science talk that ASB was putting on, and Kota Takahashi gave this advice, and I thought it was such a great way if you're nervous about going up to people in person is shoot them a note beforehand and say, hey, I would love to talk to you about this paper. It's really integral in my dissertation. Do you have 15 minutes during the coffee chat on this day to talk with me? So if you're nervous about introducing yourself to someone in person, you can always try to do it ahead of time. And that is going to be the end. Thank you for listening. Wanted to thank the two grad school co-authors that were on this paper with me, especially Paul. I threw in a little screenshot here. Paul fueled me for the first year of my PhD by constantly making coffee in the office and telling me when it was ready. So he was a great mentor in making sure I was fully caffeinated for grad school, and this awesome undergrad researcher, Courtney Smith, that I got to work with. And my lab, these are the two labs together last Christmas. So this has been a really great group to work in. So thank you, and ask me anything if we still have time, if I left enough time for questions.
We do have a little bit of time. I am going to stop the recording just so that our last few minutes, anyone can ask a question. So let me do this.
I went way too long.